the modeling of a hydraulic system. So if we could take a look here, on the left hand side you have a reservoir, and it has a pipe that goes to the turbine here, and in here you have a situation where the water is flowing here and the turbine is working normally. But what about if there is a power outage? So the turbine will spin up in here. We need to devise a system with these standpipes in here, that if we close the gate, the valve over here, the system won't explode, and also it will have, the water will have some place to go. So let me disappear here, and then we'll continue on. So right now we have this system, and what we need to do is to be able to recognize the kind of elements that we have and then do the model. So to recognize the kind of elements we have, let's try to write down in here, and then we'll just see. Okay, there we go. So what kind of element is this one over here? This is where this is, is flowing to the turbine. The turbine is like one of those turbines like this, that rotate and just receives the water here. So let's say that this is the place where they receive, but we could ideally say I have a control valve over here, and what I'm going to do is I am going to with this control valve, I am going to control the flow. So we're going to control the flow. So what kind of elements do I have? The element that I have on this pipe is a C element over here, which is the standing pipe, and in here in the pipe I would have some inertia as well as some resistance over here, and over here I also would have inertia and resistance over here, resistance to the flow of water. This thing over here is going to be a C element here, and of course the source of pressure here is going to be an SE at this point. Now one thing here is that this is the difference, this is the pressure due to this height, but down here there is a difference. There's also a source of effort which we need to account, which is the hydrostatic pressure way down there, and so is that we have also on this side over here we have a source of effort in here which considers consider the situation where you have this farther deep down pressure here. So it's I guess you can see this mouse good and this cursor good. Alright, very good. So this is what we have. So we could actually potentially build the bone graft model onto the system itself. and we could give it a try to do that. And then sorry, let's just so that we can annotate this. This is over here. Okay, we could try it like we did last time, build a model on the system here itself. So I could say, you know, here there is a one junction like this, yeah, and then you could say in here there's another flow, a one junction over here, and there's one over here, yeah, there you go. Attached to this, we will have to put the elements in here, the step number 2, and I would say that, you know, if you want, you know, attach here, this would be the source of effort here, which is the hydrostatic pressure here, and the I element over here, and therefore also this R element, which would be the resistance of the pipe. And in here we also put the inertia element over here and the resistive element over there, yeah. And in here also we have an R element, which is the one that controls everything. So this is to put the control on this R, you usually use the symbol, okay. And in here, of course, this is open-ended to, this is like a source of flow, let's see, in here there's the atmospheric pressure, so it's like F for source with E equals to 0. That's what this is. Or we could use it to control the flow in here, in which case it would be a flow source. Actually that's better, because in here it shows that it's not just to the air, but it is controlled. So we continue to try to model this thing. This is would be a zero junction where you have this flow minus this one will produce a flow 1 to which the C element is attached, the tank. And we'll do the same thing over here. 0. In this case, you could actually do just this. And of course, we will have to put this one here, the source of effort. And this will have to be the sum of two of those. So let's see how we did with the bone graft model over here. Let's just do that and say okay, this is my bone graft model. This one here is a little different than the one I did, in the sense that what we are considering here, we could do a control resistor, or you could do this source of flow. Okay, and then of course the C element, the C, the R are the same thing. In the one that I did, I didn't have two of these. I had one. Yeah, so in here we have, see the zero, this is all through power. It's like you have two sources in there. And you still need, okay, there we go. So this is the, let's see, just to make sure that we are on the same page. See here, the only difference with what I have is that this has the other component, or you could understand this to be double here. Other than that, the bone graft model is the same as this. Okay, so now what we need to do is we just run this and enter it into the CAMG software like this. What will happen is you need to go on the files, we need to edit, because the control system of that valve, this one right here, is like a control resistor in there. In other words, the valve, everything is being replaced by this. The way we simulate this is that you will have a source of flow that is controlled, and that's what I want to talk to you about, because that source of flow, that control, follows this logic. See, so this is just like we would have a let me explain over here. So this situation of the closing of the valve, here's the way I see it. All right, you have a let's see, let's draw in this is the source of flow in here, you know, at the valve. Okay, now what's gonna happen is that you have a value for a while up to a certain point, and then from here, what's happening here, then you want to close this. And follow this function. So the question now is, how are we going to do this? Let's say we're going to establish that this is, let's say, 100 seconds, and this would be 101 seconds. So we make it that that gate needs to close very quickly. So for that reason, we implement this algorithm in here that says for t from 0 to 200. If t less than 200, make this, a positive one. If f8 is less than 200, that will cover this top. Then it says between 0.1 and 0.15 or whatever. In here you have this curve, like I had it on my sniffing here. See? Okay, so like this is what I'm trying to say. See, so it is like that. So the function, just so that everybody is clear on this, is going to be like this. The red one. Okay, so if you have a situation where this is in here, there is a transition point, and from 1/10 of a second is like this, then you need to describe this. So that's what we're doing here for t is less than 100. Then make f8 equals to 1. Else if t is bigger or equal to 100, and also the other gain in here, and t is less than 101, then make this equation. This equation is the equation of this line. Okay, so you say else if do this, otherwise SF8 equals to 0. This is the way you implement this function into the CAMG software, and you have to do it on the on this resistor element in there. Okay. So once you have done this, you should be able to make this test. Whether you have a, you see from 0 to 100, nothing happens. When you close the gate and your surge tanks are 0.4 meters, you will get this.
So the scope for those would go into the capacitor flow lines in the block diagram?
I'm sorry, say that again?
So to get those graphs, you would put your scope on the flow line of your
SF8.
capacitor.
I gave you the bone normal, so SF8.
Yeah, for the block diagram.
Right here in the right there, where you make this, the plots of this element, the effort and the flows. That's so.
No,
because we need to specify SF8, that's what we need to do this. That's why I gave you.
Yeah, for the block diagram.
Yes.
And the graphs that you just showed, the water height ones,
Mhm.
you would use the flow line of the capacitors, correct?
Yeah, right there. And this would be the also this would be the pressure on the standpipes, and this would be the height. But one little trick here, From the bond graphs you get the volume, right?
So that
Because
would be
Q is
different.
volume. But I mean, Q is volume. But if you divide by the area, you get the height of the tank.
Yeah.
Yeah. So these are the plots that you will get. Like for example, a radius 0.2, you can see there's more of a response in there. And I think we have one. Yeah, we have 0.2 and yeah, this one was the. This has more stiffness than this. But that's how you get the comparison of these results and the implementation of the switch into the nonlinear modeling of the system.